Welcome to the fourth class on complex analysis. Today we introduce Cauchy product of two series and prove Cauchy multiplication theorem. Let us begin with the Cauchy product of two series. Let sigma an and sigma bn be two series. Then the Cauchy product of sigma an and sigma bn is defined as the series a0 b0 plus a0 b1 plus a1 b0 plus a0 b2 plus a1 b1 plus a2 b0 plus etc. The first term of the series is a0 b0 and the first term is denoted by c0. Note that the sum of the suffixes of the first term, that is 0 plus 0, that is 0, and the second term of the series is the sum of two terms, that is a0 b1 plus a1 b0. Here the sum of the suffixes of the first term, that is 0 plus 1, that is 1. Sum of the suffixes of the second term, that is 1 plus 0, that is 1. And note that the third term, c2, is the sum of three terms, that is a0 b2 plus a1 b1 plus a2 b0. Here the sum of the suffixes of the first term, that is 0 plus 2, that is 2. Sum of the suffixes of the second term, that is 1 plus 1, 2. And sum of the suffixes of the third term, that is 2 plus 0, that is 2. So the Cauchy product of sigma an and sigma bn is defined as c0 plus c1 plus c2 plus etc. plus cn plus etc. In general, the n plus nth term of this series cn is equal to a0 bn plus a1 bn minus 1 plus a2 bn minus 2 plus etc. plus an b0. And note that the n plus nth term of the series is the sum of n plus 1 terms a0 bn plus a1 bn minus 1 plus etc. an b0. Note that the sum of the suffixes of each term, here 0 plus n, that is n, 1 plus n minus 1, that is n. Here the sum of the suffixes 2 plus bn minus 2, that is sum of the suffixes 2 plus n minus 2, that is n. Then sum of the suffixes of the last term, that is n plus 0, is n. In compact form, the Cauchy product of two series is written as, that is sigma n is equal to 0 to infinity an into sigma n is equal to 0 to infinity bn. So the Cauchy product of these two series is defined as the series sigma cn, where cn is equal to a0 b1 plus a1 bn minus 1 plus a2 bn minus 2 plus etc. an b0. Using sigma notation, we can write this term as summation k is equal to 0 to n ak bn minus k. Note that Cauchy product of two series is a generalization of the product of two polynomials. Consider the polynomial pz is equal to a0 plus a1z plus a2z squared plus etc. an z to the power n. That is, pz is a polynomial of degree n, and qz is equal to b0 plus b1z plus b2z squared plus etc. bm z to the power m. That is, qz is a polynomial of degree n. Then consider the product of the polynomials pz and qz. Now the polynomial pz qz is a polynomial of degree maximum of m and n, and the polynomial pz qz is a0 b0 plus a0 b1 plus a1 b0 into z. Here the constant term is a0 b0 and the coefficient of z is a0 b1 plus a1 b0, that is c1, plus coefficient of z squared, that is a0 b2 plus a1 b1 plus a2 b2 a2 b0 and so on. Here we have only a finite number of terms. It is natural to ask whether the Cauchy product of two convergent series is convergent or not. We can prove that Cauchy product of two convergent series need not be convergent. For example, consider the series sigma an and sigma bn both equal to summation n is equal to 0 to infinity minus 1 the whole raised to n divided by root of n plus 1. Note that the secants 1 divided by root of n plus 1 is a monotonic decreasing sequence and converging to 0. Hence the series sigma n is equal to 0 to infinity minus 1 the whole raised to n divided by root of n plus 1 is convergent by Leibniz test. Recall Leibniz test. If the sequence an is monotonic decreasing and an converges to 0, then the series sigma n is equal to 0 to infinity minus 1 the whole raised to n an is convergent. We will show that the Cauchy product sigma an is not a convergent series. Now consider the n plus 1 the term of the series sigma cn, that is cn is equal to a0 bn plus a1 bn minus 1 plus a2 bn minus 1 plus etc. an b0. Here a0 is minus 1 raised to 0 divided by square root of 1 and bn is minus 1 the whole raised to n divided by root of n plus 1 and the second term a1 bn minus 1. Here a1 is minus 1 raised to 1 divided by square root of 2 and bn minus 1 is equal to minus 1 of the whole raised to n minus 1 by square root of n and so on, and last term an b0. Here an is equal to minus 1 the whole raised to n divided by square root of n plus 1 and b0 is minus 1 the whole raised to 0 divided by square root of 1. The above expression can be written as minus 1 the whole raised to n into 1 by root of 1 into n plus 1 plus 1 by square root of 2 into n plus etc. plus 1 by square root of n plus 1 into 1. Note that each term in this expression is greater than or equal to 1 divided by square root of n plus 1 into n plus 1. That is the first term. First term is greater than or equal to 1 divided by square root of n plus 1 the whole square. Second term is also greater than or equal to 1 divided by n plus 1 the whole square and so on. The last term 1 divided by square root of n plus 1 into 1 is greater than or equal to 1 divided by square root of n plus 1 the whole square. And note that we have n plus 1 terms. So this expression is equal to minus 1 the whole raised to n into n plus 1 divided by n plus 1, that is equal to minus 1 the whole raised to n. Now consider the modulus of Cn. Now the modulus of Cn is greater than or equal to 1. This implies that the secant Cn does not converge to 0. That is, the series sigma Cn is not convergent. If sigma Cn is convergent, then the secant Cn converges to 0. So the series is not a convergent series. Hence the Cauchy product of two convergent series need not be convergent. If sigma n and sigma bn are two absolutely convergent series, then we can prove that the Cauchy product sigma cn is convergent. Now we are ready to state Cauchy multiplication theorem. Let sigma an and sigma bn be two absolutely convergent series, and sigma cn is the Cauchy product of the series sigma an and sigma bn. Then the series sigma cn is absolutely convergent. Moreover, This series converges to the summation n is equal to 0 to infinity an into summation n is equal to 0 to infinity bn. Let us go to the proof of this theorem. First we prove that the series is absolutely convergent. To prove that the series is absolutely convergent, it suffices to show that the series sigma n is equal to 0 to infinity modulus of Cn is convergent. Now consider the sequence of partial sums of the series, that is Cm is equal to summation n is equal to 0 to infinity mod Cn. So the sequence Cn is a sequence of partial sums of the series sigma mod Cn. To prove that this series sigma mod Cn is convergent, it suffices to show that the sequence of partial sums, that is Cn, is a convergent sequence. For this, we define for each positive integer m, we define Sm is equal to set of all ordered pairs jk in z cross z such that 0 less than or equal to j less than or equal to m, 0 less than or equal to k less than or equal to m. And note that the set m is a set of all lattice points in the square 0m cross 0m. Recall that a point xy in R2 is called a lattice point if x and y are integers. For example, the points 1, 2, 5, 12, minus 2, minus 6, etc. are lattice points in R2. The point 1 by 3, 2 is not a lattice point. So the set Sm is the set of all lattice points in the square 0m cross 0m. Here this is the square 0m cross 0m. Here the blue dots represents the set of all lattice points in the square. Similarly define Tm is set of all ordered pairs jk in z cross z such that j greater than or equal to 0, k greater than or equal to 0, 0 less than or equal to j plus k less than or equal to m. Observe that Tm is the set of all lattice points in the square 0m cross 0m such that sum of their coordinates is less than or equal to m. Now consider the square 0m cross 0m. Now consider the straight line joining the points 0m and m0. That is this straight line. This straight line divides this square into two parts. And equation to this line is x plus y is equal to m. So x plus y is less than or equal to m represents this region, the lower part, and x plus y greater than or equal to m is this part. So Tm, here Tm is the set of all lattice points in 0m cross 0m such that j plus k is less than or equal to m. That is, Tm is the set of all lattice points in the triangle determined by the points 0, 0, m0 and 0. Now consider the modulus of the n plus 1th term of the series sigma Cn. That is, modulus of Cn is modulus of summation k is equal to 0 to n ak bn minus k. And note that here the sum of the surfaces, that is k and sum of k and bn minus k, is always n. So this sum can be written as summation ajbk such that j plus k is always n. That is, sum of the surfaces is always n. So by triangle inequality, this can be written as this is less than or equal to summation modulus of ajbk, j plus k is always what? Is always n. Therefore, summation n is equal to 0 to m modulus of Cn, and this is the m plus 1 the partial sum of the series sigma mod Cn. Therefore, the m plus 1 the partial sum of the series sigma mod Cn is less than or equal to summation n is equal to 0 to m, and Cn is less than or equal to this. So summation mod ajbk. Here the summation runs over all j and k such that j plus k is always n. But this summation can be written as summation mod ajbk. Here the summation is taken over all I and j such that j plus k is equal to 0 plus etc. Summation mod ajbk. Here the summation is with respect to all I and j such that j plus k is equal to m. So this finite sum can be written as summation aj modulus of aj modulus of bk such that j plus k is always less than or equal to m. But this is equal to summation modulus of aj bk modulus of aj modulus of bk, where the summation runs over all lattice points in Tm. That is, here the summation runs over all lattice points in Tm. But Tm is the set of all lattice points in the triangle determined by the points, and this is Tm. Tm is the set of all lattice points in the triangle formed by the points 0, 0, m0 and 0m. And observe that Tm, this is Tm is contained in Sm. Sm is the set of all lattice points in the square 0m cross 0m. So this summation is less than or equal to summation modulus of aj modulus of bk. Here the summation runs over all lattice points in the square 0m cross 0m. Again, this summation can be written as summation j is equal to 0 to m, summation k is equal to 0 to m modulus of aj modulus of bk. And this summation is equal to summation j is equal to 0 to m mod aj into summation k is equal to 0 to m mod bk. And this is equation 1. And observe that the series sigma an and sigma bn are absolutely convergent series. So we have the series sigma an is a convergent series. The series sigma n is absolutely convergent means the series is convergent. Similarly, the series sigma bn is convergent implies that the series sigma modulus of bn is also convergent. And this series is convergent means the sequence of partial sums of the series. Here the sequence of partial sums are sigma j is equal to 0 to m modulus of aj. And this is the m plus 1 partial sum of the series. And this sequence of partial sums is a monotonic increasing sequence. And since this series is convergent, so this sequence of partial sum is bounded above by the sum of the series. So sigma j is equal to 0 to m modulus of aj is less than or equal to summation n is equal to 0 to infinity modulus of an. Similarly, second series, that is summation n is equal to 0 to infinity mod bn is convergent. Therefore, the sequence of partial sums of this series is a monotonic increasing sequence, and that sequence is bounded above by the sum of the series summation n is equal to 0 to infinity mod bn. That is, the sequence of partial sums is bounded above by this number. Then look at equation number 1. Here equation number 1, this is the sequence of, that is the m plus 1 the partial sum of the series modulus of sigma bn, and this is less than or equal to summation j is equal to 0 to m modulus of aj into summation k is equal to 0 to m modulus of bk. But each term is less than or equal to this. The first term is less than or equal to this, and second term is also less than or equal to this. Hence, the m plus 1 the partial sum of the series sigma cn is less than or equal to summation k is equal n is equal to 0 to infinity modulus of an into summation n is equal to 0 to infinity modulus of bn. Since sigma an and sigma bn are convergent series, this product is finite, and this means that the sequence of partial sums of the series sigma cn is bounded above by this number. And note that the sequence of partial sums is a monotonic increasing sequence, and that monotonic increasing sequence is bounded above. That means the sequence of partial sums is convergent. That means the series sigma n is equal to 0 to infinity modulus of cn is convergent. That means that the series sigma cn is absolutely convergent. Absolutely convergent means convergent. So the given series, that is the series sigma cn is convergent. Here note that the sequence of partial sums cn is monotonic increasing and bounded above. Hence the series sigma cn is convergent. This implies that the series sigma cn is absolutely convergent. Next we will show that the series converges to this sum. That is, the series converges to the sum summation n is equal to 0 to infinity an into summation n is equal to 0 to infinity bn. So to prove this, consider the partial sums of the series sigma n is equal to 0 to infinity cn, and this is the m plus 1 the partial sum of the given series. That is the m plus 1 the partial sum of the series sigma cn but this is equal to summation n is equal to 0 to m, and by definition the term Cn is summation k is equal to 0 to n ak bn minus k. But this summation, so the second summation can be written as summation ajbk such that j plus k is always n. The summation is with respect to all indices I, j and k such that j plus k is always n. But this double summation can be written as a single summation ajbk such that j plus k is less than or equal to m. But this summation can also be written as summation ajbk. Here the summation runs over all lattice points in Tm. In Tm, j plus k is always less than or equal to m. So this summation is same as summation ajbk, and the summation runs over all lattice points in Tm. So summation n is equal to 0 to m Cn. This finite sum can be written as summation ajbk and jk is in Tm. That is the summation ajbk, and the summation runs over all lattice points in Tm. That is equation 3. Now consider the m plus 1 the partial sum of an, that is summation n is equal to 0 to m an, and this is the m plus 1 the partial sum of the series sigma bn. So the first term can be written as, we can replace n by j is equal to 0 to m aj, and this n can be written as k is equal to 0 to m bk. But this is equal to summation j is equal to 0 to m, summation k is equal to 0 to m aj bk. Here j runs from 0 to m and k varies from 0 to m. But this is summation ajbk. Here the summation runs over all lattice points in Sm. Therefore, summation n is equal to 0 to m an into summation n is equal to 0 to m bm. That is, this product can be written as the sum sigma ajbk jk is in Sm. That is, we are taking the summation with respect to all lattice points in Sm. Now consider the difference sigma n is equal to 0 to 2m minus summation n is equal to 0 to m an into summation n is equal to 0 to m bn. But by equation 3, what is equation 3? Equation 3 is summation n is equal to 0 to m Cn is summation aj bk j k varies over Tm. And equation 4 is summation n is equal to 0 to m an, summation n is equal to 0 to m bn is equal to summation aj bk jk varies over Sm. So using these two equations, we can write this difference as, that is the first term is summation aj bk jk varies over T2m minus, and this product can be written as summation AJBK, JK varies over SM. But this difference can be written as summation AJBK, JK varies over T2M difference SM. Note that SM is contained in T2M and T2M is contained in S2M. Here S2M is the set of all lattice points in the square 0, 2m cross 0, 2m, and that is the set of all lattice points in the square. And T2M is the set of all lattice points in this triangle. And SM is the set of all lattice points in the square. So SM is contained in T2M, but T2M is contained in S2M. By triangle inequality, this is less than or equal to summation mod AJ mod BK, JK varies over T2M minus SM. But TM is contained in S2M. Therefore, this summation is less than or equal to summation mod AJ mod BK, JK varies over S2M difference SM. Again, this summation can be split up into two, that is summation mod AJ mod BK, JK varies over S2M minus summation mod AJ mod BK, JK varies over S2M. By equation 4, the first sum can be written as summation n is equal to 0 to 2m mod an into summation n is equal to 0 to 2m mod bn. Similarly, the second summation can be written as summation n is equal to 0 to m mod an into summation n is equal to 0 to m mod bn. And we will show that when m tends to infinity, the right hand side tends to 0. Now, when m tends to infinity, the first term of the of equation 5, that is summation n is equal to 0 to 2m mod an into sigma n is equal to 0 to 2m mod bn. Note that the series sigma mod an is a convergent series. Therefore, the sequence of partial sums converges to the sum summation n is equal to 0 to infinity mod an. Therefore, the limit of the first sequence converges to this. Similarly, the limit of the second term also converges to this value. Similarly, limit of summation n is equal to 0 to m mod am converges to this value, and the limit of the second term converges to this value. Therefore, the limit of, that is when n tends to infinity, the right hand side tends to 0. That means the limit of the left hand side is also 0, but the limit of the left hand side, that is limit of summation n is equal to 0 to 2m cn minus summation n is equal to 0 to m an into summation n is equal to 0 to m bn is equal to 0. And this limit is equal to 0 means the limit of summation n is equal to 0 to 2m cn is equal to limit of this, that is limit of n is equal to 0 to m am into limit of m is equal to 0 to m bm. But the limit of the first term is summation n is equal to 0 to infinity an, and the limit of the second term is summation n is equal to 0 to infinity bm. But this is same as summation n is equal to 0 to infinity cn. Note that sigma mod cn is a convergent series. Therefore, sigma cn is absolutely convergent. But absolutely convergent means convergent. Therefore, the sequence of partial sums of the series sigma cn converges to the value summation n is equal to 0 to infinity cn. That means the Cauchy product series converges to the sum summation n is equal to 0 to infinity an to summation n is equal to 0 to infinity bn, and this is the sum of the first series and this is the sum of the second series. So the Cauchy product series converges to this value.